Hello all, welcome back to part 3 of lesson 3 for Calculus AB, where we're finding limits analytically. In the first video, we talked about the technique of direct substitution and how to find a limit using factoring when we have indeterminate form. In the second video, we did some more indeterminate forms with multiplying by the conjugate, combining fractions, and expansion in the form of FOILing. And in this video, we're going to talk about one-sided limits and some basic limit laws. So let's first of all talk about these 4 questions here and do some strategies on what's going on. So for question number 10, it says the limit as x approaches 0 from the right of 1 over x. So question 10 and 13 are very similar for the fact that these are parent functions that you should already know. So if we graph these two functions, I'm going to go ahead and do both of these kind of slightly together. So 1 over x looks like this function, right? So it's just the parent function. 1 over x looks like this. Now, I just want to address really quickly that this little superscript right here, this plus, just means that it's a right-hand limit. So we've actually talked about this before. If this problem had said the limit as x approaches 0, just flat out 0, then there would be an asymptote here. You guys know that this would not exist because it's not continuous at x equals 0. Therefore, the limit doesn't exist there because it would be infinite discontinuity. So there is an asymptote that we can see here at x equals 0. And so what the question's asking us is if we're approaching it from the right. So as we follow our function to the right, what's the behavior of our function doing? Well, as it's approaching to the right, it's going up, 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 and up, and it's actually approaching positive infinity. So this answer is positive infinity. If this had said the limit as x approaches 0 from the left, right, the left, then we would go in this direction, 0 from the left, on the left side of 0, and it would be negative infinity. And then the other thing we've actually done with these problems is what happens if it was the limit as x approaches positive or negative infinity. Well, as they're approaching positive or negative infinity, we would go to 0, the answer would be 0, because again, this is a bottom-heavy function, right, bottom-heavy function. So it's a lot going on in this particular example, and a lot of answers we could do based on what you guys see down here. But again, this is a right-hand limit, so we're just looking at the right-hand side, so I didn't even need this part of the graph, right, because I'm just caring about what's happening 0 to the right, and so the answer, again, is positive infinity. So I'm going to jump down here to question number 13 and look at this one. So this is the parent function of the absolute value of x over x, which looks very similar to this, right? You guys know this graph looks like this, where this is -1 and this is +1. Well, the -3 that's inside of the absolute value is actually just transforming it or making it move 3 units to the right. So 1, 2, 3. So we're 3 units to the right, and our graph is going to look like this, where this again is still 1, and this part here is going to be -1, right? This part here is -1. So just like in example number 10, it's asking us to find x approaches 3 from the right. This is the right-hand limit. So just like we've done in the previous example, we're looking at 3, right? So here's our x equals 3, and we're looking at just from the right. So we're following our function as x equals 3 from the right. And so this corresponds with the value of 1. If this had been x approaches 3 from the left, then we would have went from the left-hand side, and this answer would have been -1. If it just had the limit as x approaches 3, flat out 3, then the answer is going to be does not exist. And you guys know this, we've talked about this before, that the right-hand limit and the left-hand limit are not equal to each other, right? The right-hand limit is 1, the left-hand limit is -1, therefore the overall limit cannot be defined. So right-hand side is 1, left-hand side is -1, and the overall limit is 0. Okay, so now let's look at question number 11 and number 12. So they're very similar as well, with just a little bit of a difference. Notice that for this one, again, we're looking at x equals 2 from the left. And if we were to graph this function, and I'm not going to spend time doing it, but if we were to graph this function, we already know that at x equals 2, we would have a horizontal asymptote, or a vertical asymptote, right? A vertical asymptote. So what I know is going to happen is that my answer is either going to be positive infinity or negative infinity. As I'm approaching 2 from the left, either my graph is going to be going in this direction here, or it's going to be going in this direction right here. I don't know which one exactly. So I have to have a strategy to figure out which one this is. So yes, technically does not exist is a good answer here, but most of the times these would be multiple choice, and does not exist would not be an answer choice. So we're going to show you how to do it either being positive or negative infinity. The one thing I just want to notice really quickly about number 11 that's different from number 12 is that if I plug 2 into the numerator, I actually do not get 0. right? I do not get 0 over 0. I get some number over 0. Now, if this had been x approaches 2, this answer would be does not exist because you have a number over 0, and we talked about that in the second video. But since we're looking at the left-hand side, I want to know, is it positive or negative infinity? So what I do, and this is my side work, is so if I'm at 2, I want to be on the left of 2. So I want to choose a value, a number that's really, really close to 2. So I'm going to do x equals 1.9. That's really close to 2 on the left-hand side. And all that we do here, ladies and gentlemen, is we're going to plug in 1.9 everywhere we see an x, and we just want to look at the sign. I don't care what the value is. I know that 1.9 minus 1 is a positive number, and obviously multiplying it by 3 is also a positive number. I know 1.9 minus 2 is going to be a negative number. Therefore, I know that this is going to be positive. The behavior of this function is going to be positive over negative, which means that it's going to end up being negative. So the answer is negative infinity. So my value is, and I want you guys to think about it. This is 1.9 right here. And I know that I'm at a negative value, right? Because I just found it. It's a negative value. And the direction, remember, it's really, really, really close to 2. So it's negative. It's not going to go up like this, right? It's going to come down like this. So it's approaching negative infinity. And if you wanted to do another like 0.99, right? 99, that's still going to be negative, right? This is still going to be positive. I could have an infinite amount of 9s here. It's still going to be 1 point something. It's greater than 1, right? And this is always going to be negative. So no matter how big we get or how close we get to 2, it's going to be positive or negative, so the answer is negative infinity. And so that's what you do for that particular problem. So let's look over here at this graph. We plug in 8 at the bottom. Okay, yes, we get 0. However, we plug in 8 here, we also get 0. So there's not an asymptote there like it is in this one. So what we want to do is you always want to check with substitution first, even with these limits. So since this is 0 over 0, I can go ahead and simplify the top as x minus 8, x plus 8. And then you guys can see that I can cancel these out. So this overall limit, the limit as x approaches 8 from the right, is just x plus 8. And so I can go ahead and directly substitute in, and I can get 16 here, and this is actually the answer to this problem, because there's a hole. There's a hole at x equals 8, right? There's a hole at x equals 8, and the corresponding y value is 16. So what this graph looks like is when we're at x equals 8, I have a function coming up, and then I've got a hole here. And you guys learned from lesson number 2 that this is what we call removable discontinuity, all right? Because there's a hole in it, and you know that for all removable discontinuity, the limit will exist. So why can I go ahead and plug in 8 to the right? Why did I go ahead and plug in 8 when it's 8 to the right? Well, good. If the overall limit exists, right? If the overall limit exists, then the right-hand, left-hand limits have to also exist, and they have to also be the same values. So that's why I was able to plug in 8 here and not have to do 8.1, because students always ask, why not 8.1? I'm not worrying about that right now because I'm looking at the overall limit, right? This is because both of these end up being 0 over 0, so it's an indeterminate. So those are your 3 different types. Parent functions, where you actually truly have an asymptote, and again, it's where you get a number over 0, but you have to remember, again, that it's a right or left-hand limit here. And then this one right here would be, obviously, if it's 0 over 0, you can simplify this down first before you start doing other things. And you could absolutely simplify this down, and there still be an asymptote, and you still have to do this method, but in this case, we don't have to do it. Okay, so I'm going to jump now. I know this is going to be kind of weird, but I'm going to jump from now this to limit laws. I'm jumping here to limit laws now. All right, so we now have a general idea of what a limit is and how to find them algebraically. So these are a couple of just helpful, useful things for us to look at. And so let's go over these a little bit more in detail. And like I said, I like to use actual examples. You don't need to know the names of these things, but the first one is this. So I'm going to go ahead and just call this A. And this is going to be the limit as x approaches. And I'm going to do 5 of the number 9. Okay, the number 9. And so what this really means is that what is this limit? So what you want to know is that if you're taking the limit of a number, the answer is always going to be that number. And that's all the constant rule says. And guys, I want you to visualize that for a second. So if I ask you guys to graph this, and it's okay, let's look at y equals 9. So let's just say this value here is 9. It doesn't matter where I'm approaching this line, right? It doesn't matter if here's x equals 5. Well, if I go up here to x equals 5, the behavior on the left and right are 9. I could go over here to -3, and again, the behavior is 9 and 9. So no matter where on this line we are, no matter where we are on the x-axis, no matter what x we're approaching, all of our y values are going to be the same, right? Hence the equation y equals 9. So this answer is going to be 9. So when you're taking the limit of a constant, no matter what this is, whatever this is, it's going to always be the constant. So that's what A is telling us to do. B is the limit as x approaches 3 of x. What is that? Well, again, this is classic substitution. If it's x, it's just going to be equal to 3. And again, think about it like this. This is going to be y equals x, right? Y equals x. And so then you're looking at the function y equals 3. So you just do a direct substitution problem for this. Okay? Direct substitution for this. So hopefully that makes sense to you guys as well. And then the coefficient rule is, let's go with that with our letter C. So C, I have the limit as x approaches C of, let's say, 5 times f of x. Now, I don't know what f of x is yet, but the whole point of this is I can pull the 5 out. So you can always pull it out, and then take the limit of f of x as approaching C and then multiply it by 5. Okay, and that actually gets very similar to what you guys can see with the product rule. So the product rule is actually kind of the same thing. You could have, so this is f, and I'm going to put it right underneath it here. So for f, if I took the limit as x approaches C of 5, and I multiply that by the limit as x approaches C of f of x, well, we've already discussed what this is, right? We already talked about that right here in A. This is going to be 5. Right, so this whole thing right here is equal to 5, and so it's going to be 5 times this limit. So that's why you're able to pull the constant out, because the limit of that number is just that number. So that's why f will work. And then D and E are, if you take the limit of, let's say, x approaches 1 of 3x plus x squared. Now you guys know you can absolutely substitute in, and that's the easiest and most efficient way of doing this problem. However, what you could also do is take the limit as x approaches 1 of 3 of x, and then add the limit as x approaches 1 of x squared. Plug in, you get 3 here, you plug in 1 here, you get the answer is 4. And you already know the answer is 4 because of direct substitution. So that's why you're able to plug in 1 here and plug 1 here and work on them. And the difference, instead of being a positive, it would just be a minus. So most of these things are pretty straightforward. And then the quotient rule one is very similar to the product rule one. If you're taking the limit of two functions here, you want to make sure that you take the limit of f of x and divide it by the limit of g of x. This is not a natural log thing. Students always get confused with this, and they think it's the limit of f of x minus the limit of g of x. That's if you're thinking about the natural log. So you take the limit of f of x, the limit of g of x, and you divide them, and you get the value here. And this obviously is assuming that the limit of g of x is not equal to 0. Okay? That's really what you need for that. The power rule we're going to get to a little bit later on in life, so we'll do that one later. And so this last little example, ladies and gentlemen, is really straightforward. It's the application of your limit laws. It's telling us in it's telling us in the problem that the limit as x approaches b, I don't know what b is, but it's okay, of f of x is equal to 7, and the limit as x approaches b of g of x is negative 3. So the first thing that I can do here is I can say, well, let's look at this one. Well, this would just be the limit as x approaches b of f of x plus the limit as x approaches b of g of x. All right, that's simple. That's simple. And we automatically know that this is equal to 7. We automatically know that this is plus. This is equal to negative 3. So this answer is going to be equal to 4. Okay, pretty straightforward. If I look at example B, it's going to be the limit as x approaches b of f of x times the limit, and you don't really have to show work here. I mean, we all can do this in our heads, but it's just to show you the limit laws. And so it's just multiplying these two together, and so that's just going to be 7 times negative 3, which is going to be equal to negative 21. So the limit of the composition. And then for example number C, we can pull out the 5. Right, we can pull out the 5 and just do this function right here. Well, we automatically know what the limit as x approaches b of g of x is. It's negative 3. So this is going to be 5 times negative 3, which is negative 15. And it's pretty straightforward. And then it's not always this direct. I will tell you guys right now, in BC calculus, we do examples where what happens if we're at a piecewise function. So what if this approach is a piecewise function? It does require a little bit more thinking than this, but for this particular class, this is really as hard as it's going to get for you guys. And let's be quite honest, this is not hard at all, right? So it's just really awesome that you can do individual limits, right? And then just actually put them together. So that would just look like this. The limit of f is 7. The limit of g is -3. So your answer is -7/3. And last but not least, it's telling us to find the limit as x approaches 2 of f of x plus of x. So you guys know that this and this is very similar to each other, so I can rewrite this problem out pretty well. So this is going to be the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. And so if we're looking at f of x, remember guys, and we're going to keep doing this as we're approaching 2 from the left to the right, I'm at a hole. The limit still exists. It is still equal to 1. It's still equal to the corresponding y value here. It doesn't matter what this point is. Remember, f of 2 is equal to 3. So it's not continuous at x equals 2 because there's a hole there, right? But the limit still exists because it is still removable. And I gotta keep stressing that, right? It's still removable. So removal discontinuity still means the limit exists. Our behavior around x equals 2 is still going to be equal to 1. And so that's what 1 is, and then plus, and again, we're going up here, and we're going to see from the left to the right, we have a value at 3. So this limit is 3. And so this answer would be equal to 4. Okay, this is equal to 4. And that finishes up lesson number 3 for Calc AB. So in the next video, next lesson, we're going to talk about we're going to talk about continuity and how to write that properly. And then lesson number 5, we're going to do our good old friend, the IBT. All right, so I'll talk to you guys in the next video.